In this lesson, I want to try to explain how the van der Waals forces impact the way we think about alkanes. The van der Waals forces are the forces that exist in between separate molecules and kind of glue them together. And it accounts for the general stickiness that occurs between molecules. And this is manifest by things like surface tension of water. As water has a high surface tension because the water molecules themselves stick together via van der Waals forces, or boiling point. Molecules with a higher boiling point are harder to separate and push into the gas phase because they have stronger intermolecular forces of attraction. These intermolecular forces of attraction, that term is kind of, it's a lot to say, so we just refer to them as IMFs. So van der Waals forces, or IMFs, can be broken loosely into three categories. You have dipole-dipole, dipole-induced dipole, and then induced dipole-induced dipole. Again, a lot of words that you have to say, so we come up with other terms. This dipole-dipole attraction is one that we'll talk quite a bit about, and hydrogen bonds fit inside of this category. This one doesn't gather as much attention, so we'll kind of skip over this one. But the third one here, induced dipole, that's referred to as London or dispersion forces. And some textbooks refer to it as different things. I'm going to call this third one here dispersion forces. So let's start off with dipole-dipole attractions, and I'll cut right to hydrogen bonds. So this kind of represents the structure that water molecules have a tendency to make. The oxygen in a water molecule carries a strong partial negative charge, and that partial negative charge is permanent. The oxygen is always winning the tug of war for electron density with the hydrogens, so it's going to pull electron density on top of itself, generating a partial negative charge. That comes at a cost of the hydrogens having a partial positive charge. And so the partial negative charge on the oxygen starts to interact with the partial positive charge on the hydrogen, and this is your characteristic hydrogen bond. Whenever you're looking for hydrogen bonds, you want to be sure to find three atoms. You find a hydrogen in the center, and on one side that hydrogen is surrounded by typically an oxygen, nitrogen, or fluorine, and on the other side the hydrogen is covalently bound to an oxygen, nitrogen, or fluorine. So in order to identify a hydrogen bond, you look for these three types of atoms. Hydrogen in the middle, bound to a nitrogen, oxygen, or fluorine, and interacting with a nitrogen, oxygen, or fluorine. And water can form a series of hydrogen bond interactions. As you slow the water molecules down and they start vibrating less, then the waters will kind of lock down in this hexagonal arrangement. And this is kind of the structure of ice. And it explains why the density of ice is lower than the density of water. This hexagonal arrangement causes the water molecules to spread out to maximize their hydrogen bond interactions. So hydrogen bonds are our special class of dipole-dipole attraction, the strongest class of dipole-dipole attractions. If we look at just another kind of a regular dipole-dipole attraction, and that occurs anytime you have a permanent partial positive interacting with a permanent partial negative. So the bond between, this is nitrogen monoxide without any lone pairs, and the nitrogen is less electronegative than the oxygen, so it always carries a partial positive charge. The oxygen would always carry a partial negative charge, and you can kind of see how these molecules would stick together. Now, because these are very small molecules, it's hard to get them to hold still. You have to cool this compound way down in order to start to form these dipole-dipole attractions. And this means that the molecule actually, even though it has fairly strong dipole-dipole attractions, still has a very low boiling point. Just because the molecules are so small, it's easy for them to kind of escape. All right, enough about dipole-dipole attractions, of which hydrogen bonds are definitely the most important category. Let's move on now to the dispersion force, which is also called London force, or the induced dipole attraction. Okay, imagine you have one atom over here, and here's the nucleus of this atom, and then you have the electron cloud of this atom. The nucleus of this atom kind of corrals the electron density, but the electron density, especially for larger atoms, is held loosely and can wander around a bit. It kind of sloshes around the nucleus a little bit. Whenever the electron density kind of shifts over to one side or the other, you actually end up with a momentary dipole. So right now, there was a partial negative charge over here because the electron density leans over to this side. So now there's that partial density of negative charge, and now a partial negative charge. If we look at that same time, but from the perspective of the nucleus, there's a partial positive charge that kind of gets exposed on the nucleus. When the electron density slides away from the nucleus, now you have a partial positive charge over here. So now, and now, and now. All these times are when the nucleus is kind of uncovered and the electron density leans away. This flashing that you're getting over here is the rest of the animation. When you have a lot of atoms and you start packing them together in a solid state or in a liquid state at lower temperatures, what happens is the partial negative of the electron cloud leaning over to one side will push on the electron cloud of the neighboring atom. And that causes all of these electron clouds to start to oscillate in harmony with each other. And there's a moment here when the electron cloud has leaned over as far as it can to one side and caused the nucleus of the neighboring atom to be exposed, that you have a partial negative on the electron cloud interacting with a partial positive on the neighboring nucleus. And this is just a kind of a transient moment. It happens quickly, and then the electron cloud slides back, and you get that same effect on the other extreme. This type of oscillation is what's referred to as an induced dipole-induced dipole attraction. So induced means you're causing it to happen. You're causing a dipole to occur by pushing the electron density to one side, and then that sticks to the neighboring atom, which has also been polarized by the electron density sliding over to one side. So this is the classic dispersion force interaction. And this is what happens when you think about alkanes. Alkanes are not polar. They can't make hydrogen. They're not very polar. Well, they're overall not polar. It's complicated. I should edit this out. Just ignore that. The alkanes themselves have no net polarity. That's the best way to say that. But they do have an electron cloud. And so if you kind of envision this electron cloud as this kind of this sloshing density of electrons, it's kind of oscillating back and forth around the various atoms. So it just kind of swings around the atoms. And that electron cloud can line up with a neighboring electron cloud, and now you end up with two of these electron clouds that are moving together. And so you think about with alkanes, the electron clouds of these alkanes start to synchronize in terms of their motion. And this causes the alkanes to form liquids. It's the type of interaction they're having when they're a liquid, and it's also what's going on in the solid state. That underlying dispersion force interaction is what causes alkanes to kind of stick together. And the more the alkanes stick together, the better they kind of sit on top of each other, then the more you're going to maximize that dispersion force interaction. And so this is 1, 2, 3, 4, 5, 6. Here are a bunch of linear hexane molecules. They are stacking together reasonably well, and you expect hexane to have a boiling point that reflects the ability of hexane to stack together. If things stack together well, then that means that they form strong dispersion force interactions. It's harder to break those apart, and so you end up with a higher boiling point. Okay, so now we can get into the lesson. We've already answered a few of these questions. So first of all, intermolecular forces. We want to provide a descriptive explanation here. And these are the forces of attraction between different molecules. And we'll come back and look at physical properties and chemical properties in a second. Here is the listing of those three different types of intermolecular forces, or the three types of van der Waals forces. There's the dipole-dipole, of which hydrogen bonds are kind of this extreme case, the strongest case. Dipole-induced dipole, which we don't really talk about, and then induced dipole are the dispersion forces. So the question asks, what type of intermolecular force dominates in the interaction between water molecules, and explain with appropriate diagrams. And I showed you this example on ChemDraw. We looked at water molecules and how they're held together with hydrogen bond interactions. And then the second question asks what type of intermolecular force dominates in the interaction between hexane molecules, explained with appropriate diagrams. So hexanes, like all alkanes, are primarily held together by dispersion force interactions. Remember, dispersion force interactions are this third type, the induced dipole-induced dipole. And that involves the oscillation of electron clouds, which occurs best when the molecules can kind of pack up next to each other, and it maximizes the surface contact between the molecules so that their electron clouds can oscillate in harmony. The next part of this lesson asks us to now take our understanding of intermolecular forces and start applying it to a consideration of boiling points. So here I have 5 different compounds and 5 different boiling points, and I need to match them. And they're currently not necessarily lined up. So I'm not saying that the boiling point of isobutane is 261 Kelvin. So now I kind of need to order these things. The first and most important criteria when ordering boiling points for small alkanes is simply the number of carbons. So if you consider this example right here where we stacked all these hexanes together, you can also look at butane. Well, if you stack butane together, you can still get kind of a nice interaction between the butanes, but the molecules are much smaller. And when the molecules are smaller, there is less surface area over which 2 different molecules can interact with each other. And so when you're ordering molecules, alkanes specifically, in terms of boiling points, the most important factor is the number of carbons. At some point, the number of carbons becomes a less important factor. Once you get out to 10, well, maybe 15 or 20 different carbons, then there's other factors that start to dominate. But we're going to stay with small alkanes, and for the examples that we're going to see, the most important factor is the number of carbons. So if we go back here, isobutane has 4 carbons, isopentane has 5 carbons. So I'll just make a note right here. This is a 4-carbon compound. This is a 5-carbon compound. N-butane, remember that N is that old-fashioned system of nomenclature where it just means a linear version. And if you left the N off entirely, it would still be the same molecule. Neopentane has 5 carbons, and then N-pentane would have 5 carbons as well. Whoops, there we go. And the N, again, just tells us that we're talking about a straight chain, and it's exactly the same just to say pentane. Okay, so the most important factor is the number of carbons. So I have 2 4-carbon compounds and 3 5-carbon compounds. So these 2 4-carbon compounds are going to have the 2 lowest boiling points, and the 3 5-carbon compounds are going to have the highest boiling points. So let me draw isobutane and butane and think about which of those 2 would have the lowest boiling point. So let's draw butane, which I just had a bunch of them, and then I'm going to draw isobutane. If you remember, isobutane has a systematic name of 2-methylpropane. It's one of the common names that you need to know. What you're doing when you're thinking about dispersion force interactions is you can also think about that in terms of the stackability. If I'm trying to make a wood pile and this is what all of my pieces of wood look like, then I can stack this together nicely. And you make, and they kind of shift. They don't necessarily behave as well as this. You might end up with some of them that look like this, and then maybe a particularly poorly behaved ones that does this. But for the most part, you're going to expect these things at low temperatures to kind of maximize their interactions. And they start stacking together very nicely. That increases the surface area over which they can form dispersive force interactions and glues them together more tightly. And this means that you're going to have a higher boiling point. It's going to be harder to break these things apart and push them into the gas phase. So higher stackability, and it doesn't really matter how I spell this because I'm absolutely making up this word, is equal to a higher boiling point. Now consider trying to do the same thing with isobutane. And the problem is that they just don't, and this is actually a tetrahedral compound, so it's got some 3-dimensional shape to it that I'm ignoring, but you really can't put these together in a very easy fashion. It's, imagine trying to make a wood pile out of a bunch of branches that had things sticking off the side. And so what this does is it produces a case where we have essentially lower stackability. The molecules don't stack together very well, and so they would have a lower boiling point. It would be easier to heat this up and get one of these isobutanes to kind of break free from your wood pile and pop off into the gas phase. So going back to the problem here, the isobutane is the one with more branches. And so the isobutane is going to have a larger problem stacking and won't stack together very well, so it's easier to boil it, so it will have a lower boiling point. So this is correctly lined up already for us. The isobutane is going to have the 261 Kelvin boiling point. The butane, remember the most important is the number of carbons. So because the isobutane and the butane have 4 carbons, we know they're going to get the lowest 2 values. After you've divided these things up based on number of carbons, then we evaluate stackability. If things stack together better, then they're going to have a higher boiling point because it's harder to break them apart. Normal butane or linear butane stacks together nicely because the molecules are lined up for you, and so we end up with a slightly higher boiling point right there. Now we're ready to go through these 3 different 5-carbon compounds. The linear one is definitely going to have the highest boiling point of those 3. And so I'm divvying up these 3 boiling points right here, and the linear one, the N-pentane, is going to have the highest boiling point. To look at which one would have a higher boiling point between isopentane and neopentane, it's helpful to think about the structures. Isopentane is a common name, and it looks like that. And then this is neopentane right here. It looks like that. And the neopentane is going to have all kinds of problems trying to stack. There's really not any surface where it's going to have a good interaction with, it's like stacking a bunch of rubber balls together, and the surface contact is minimized. The isopentane does have this branch sticking out, but you can kind of imagine still maybe some ability to stack. If we flip this around, we can get some good stacking right there maybe. And so the isopentane isn't quite as branched. It just has 1 branch. The neopentane has 2 branches. The 2 branches are going to disrupt the ability of the molecules to form strong dispersion force interactions, and so that means it's easier to break them apart, they're less stackable, and they'll have the lowest boiling point. The neopentane does not have enough branches to lower its boiling point down into the range of 4 carbon groups, but it gets pretty close. So it's going to have the 283 Kelvin. And then what do we have left? The isopentane is going to have the 301 Kelvin. You can imagine a case where you build a large enough alkane, and let's just make a really big one right here, and then you start introducing just a ton of branches into this thing. And you can make the branches even more creative like this, put a tert butyl group on there, and put an isopropyl group over here, and maybe another tert butyl group right there. And pretty quickly, you've got so many things coming off of the straight chain that these will stack very, very poorly. And this is why, for small carbon-containing compounds, the number of carbons is the most important criteria. But as compounds start to get very large, the number of carbons is less important. And so I'm going to avoid all of these examples when I ask you to predict the boiling points. For all of the examples that you will see, the boiling points can be determined by first breaking them up into groups of number of carbons, and then after you've kind of divvied them up based on number of carbons, then you start thinking about the branching and how that will affect the ability of the molecules to form strong dispersion force interactions. The next question we want to think about is actually more about energy diagrams, but we're going to use the concept of oil and water being mixed together to illustrate this concept of energy diagrams. So consider a case, let's use this structure to draw this. A typical energy diagram, we're going to look at quite a few of these over the course of the semester, requires us to think about an x-axis and a y-axis. And on the y-axis over here, we're going to have energy. We can abbreviate energy as NRG. That's energy right there. And that's going to be our y-axis label. And the higher up on the y-axis we are, the higher in energy we're going to be. And on the bottom is, on the x-axis, is called reaction progress. And this is similar to the concept of time. Chemists like to be very specific that it's not time, it's reaction progress. but conceptually it works to kind of think about this as time. And you can imagine some process where you start off with your chemicals at some initial energy state. You have to go up in energy. This is called the activation barrier. And then you drop in energy to your final energy state. And the difference between these two, between the initial and the final energy state, is the delta H or the delta G of the reaction, depending on how you're conducting your experiment. So this is the overall energy change. We'll just call this energy change right here. And then we also have an activation barrier. And this is how much energy you have to put into the system to get it started. And you can think about this as lighting something on fire, even a puddle of gasoline, lighting that on fire. You still have to put some energy into the puddle of gasoline to get it to ignite. That's the match or the spark that you throw at that puddle. So that's the activation energy. And then you have the energy change. So this would be your starting state, and this would be your end state. And we usually just call this the reactants, and this over here would be the products. So just a basic energy diagram. And so for the process of water and oil, water plus oil, and you're going to mix those together to produce a product. Let's just say a mixture of water and oil. And so the water plus oil are going to be over here on this side of your reaction. They're your starting material, and then we're going to have water and oil as the product. Only if you have ever tried to do this, and Italian salad dressing is the classic example of this, what you'll notice is that it's not a spontaneous process. And so if you actually do manage to get water and oil to come together, within just a little bit, the water and oil are going to re-separate back out again. And that's because the energy diagram, let me get rid of some of the details here that we don't need, just focusing here on the shape of the curve, it's actually an endothermic process. And so we can change the shape of this curve. And this is kind of more like what happens when you think about, water and oil being mixed together. That the water and oil are actually at a lower energy state when they're separated, and then they're at a higher energy state when you shake them together. And this activation energy, you can actually keep feeding that activation energy into the system by continually shaking it, and you can sort of get them to stay mixed together. But as soon as you stop shaking it, then it will spontaneously go to a lower energy state, and the water and the oil will separate. This concept from an energetic perspective involves two steps. Well, actually, we can break it into three steps. When you take water and oil and you try to mix them together, what you have to do first is break the hydrogen bonds of the water. You got to separate all the water molecules apart from each other. And then you also have to break the dispersion force interactions. So I want to get another. So this arrow right here might represent the energy that is required to break apart the dispersion force interactions of the oil. And then over here, this is the energy that you get back when the water and oil form new interactions. And since water really makes pretty poor dispersion force interactions, there's really not, and oil doesn't make good hydrogen bonds, you're not getting very much energy back out of the system. So it's costing you more energy to separate the water and more energy to separate the oil than you're getting back from putting the oil and the water back together again. And this kind of diagram describes any two things that you try to dissolve into each other that don't mix. Water and chalk. You can just put a piece of chalk or in water, and you shake it up all you want, and you might shatter the chalk and get them to momentarily suspend. But the problem is that the interactions that occur between the chalk and the water don't give you back the energy that it took to break apart the water from each other to disrupt that hydrogen bond network or to disrupt the ionic interactions that are holding the chalk together. And so it just kind of slides back to its original state. So this is kind of a description of what happens when you try to mix things together that don't mix. So draw an energy diagram to explain why water and oil do not mix spontaneously. This is referred to variably as the hydrophobic effect, and it's based on the concept that you don't get the energy back from the new interactions that the water and whatever in this case the oil would make that you spent in order to break the water apart. So this is the energy gained from new interactions on this side. We're going to complete our diagram. So this is the energy gain from the new interactions, and over here on this side we have the energy cost of disrupting the oil, and down here would be, this other arrow would be the energy cost of breaking the H bonds in the water. All right, see if we can copy and paste this over into our answers. That didn't look too bad. That'll work. Okay, this is again referred to as the hydrophobic effect and kind of explains why water can't dissolve everything. Water won't dissolve something when the energy gain from the new interactions does not exceed the sum of the energy cost of breaking apart the hydrogen bonds of water and the energy cost of disrupting whatever that solute was. All of these different features that we've talked about so far are called physical properties. And physical properties are characteristics of a molecule of molecules that can be explored without breaking bonds. And the type of bonds specifically are intramolecular bonds. These are the covalent bonds and the ionic bonds that hold the thing together. Covalent and ionic bonds. Okay? And so these are the physical properties. And everything that we've done has kind of been thinking about breaking the intermolecular bonds. Okay? So these intermolecular with an ER ending right there is different than the intra. And so we talk about the intermolecular bonds between hydrogen, between water molecules, but this was kind of really where we explored physical properties. Boiling points are physical properties because it's still the same compound regardless of whether it's in the liquid state or it's in the gas state. It's still isobutane or isopentane. And water and oil are still the same regardless of whether you're shaking them to keep them together or you're separating them apart. So the next thing I want to think about is chemical properties. And this is characteristics, let's see if I can spell it correctly this time, of molecules that can be explored by breaking these bonds, by breaking these intramolecular bonds. And I'm going to underline this just to make sure that you know I'm not talking about these IMFs, molecular bonds. Okay. And so we're going to start to react to these things. We're going to combine them in new ways, and we're going to think about how they behave. For example, the chemical property of sodium metal is that when you add it to water, it usually kind of creates an explosion. It rearranges its chemical bonds to form sodium hydroxide and hydrogen gas, and if you've seen that demonstration, it's kind of fun to watch. The most common type of chemical reaction that we use to explore the nature of alkanes is a combustion reaction. When you set fire to a hydrocarbon, something that contains hydrogen and carbon, like an alkane, you're burning it by combining it with oxygen, and you're going to generate carbon dioxide and water as your major products. When we do that, you'll notice that we end up producing some amount of heat. So this is how a gasoline engine works, a propane stove, central heating with a natural gas furnace. In all those cases, you're just setting fire to hydrocarbons and you're generating carbon dioxide and water. What you'll notice with both isopentane and pentane is they have the same molecular formula. This means that they're constitutional isomers of each other. And when you burn them, you combine them with exactly the same number of oxygens, 8, and you produce exactly the same number of carbon dioxides and waters, 5 and 6 respectively, but you don't get the same amount of energy out of that process. And in fact, what you'll notice is you get slightly more energy, and negative means it's giving off energy, so you're getting off 5 more kilojoules per mole when you burn pentane than when you burn isopentane. And when you burn hexane, you get 600, it's about 700 kilojoules per mole more when you burn hexane than when you burn either of the 5 carbon constitutional isomers. And this brings back something that we saw with boiling point. that the most important factor in the examples we're going to look at is the number of carbons. Let's look at an energy diagram for the combustion of a pentane. Now, I'm not going to specify right now whether or not it's isopentane or N-pentane, but let's just think about burning 5-carbon compounds. We can use kind of the same idea of an energy diagram here, okay? Only now I'm going to go ahead and just clean this up a little bit. And if you burn something, you're going to get net energy out of the system. So instead of being an endothermic process, now we're looking at an exothermic process. And we still have kind of the same process. Here is the activation energy associated with the reaction. And then we have, this is the, we'll talk about this arrow in just a second, but this is the total energy associated with the reaction. And that's that delta H that I showed you before. So what's going on right here in this activation barrier is this is the energy cost of breaking everything apart, breaking bonds. In order to get in order to get pentane to react with oxygen, you have to kind of pull apart all of the carbon and hydrogen and oxygen atoms, and that has some associated energy cost. It's always going to cost you energy to break apart bonds. And then on the downslope right here, this is the energy gained from the new bonds that we make. And the reason that the reaction is overall exothermic is because you gained more energy by forming 5 molecules of carbon dioxide and 6 molecules of water than you lost by stripping apart 1 molecule of pentane and 8 molecules of oxygen. So that explains why this process is exothermic. That you got more energy back from the new bonds that you made than it cost you to break the old bonds. What we really want to focus on, though, is the total energy change. And so this energy change is the difference between the amount of energy we started with. So I'll just draw a horizontal line here to kind of show you that there is some energy starting point and then there's some energy finish point. And the delta H associated with this reaction is the difference between where we started and where we finished. And this is important when you're thinking about, there's actually 2 different types of pentane. If I take 5 carbons and try to build them, well, there's actually more than 2 different types of pentane, but there's 2 different types of pentane that we're exploring in this particular example. We're looking at isopentane and then N-pentane, or just pentane. So this one is called just pentane, and here we have the isopentane. When you set fire to either isopentane or pentane, you end up with exactly the same products either way. And carbon dioxide does not have any constitutional isomers. There's no other way of really drawing carbon dioxide than you have a carbon in the middle and 2 oxygens on the outside. And water also doesn't have any constitutional isomers. It's just a single structure. So energetically speaking, whether I decide to burn isopentane or pentane, I am going to get to the exact same end point. And so this point right here will be the same for both of my constitutional isomers when I burn them. And therefore, any difference that I see in this delta H value has nothing to do with the end point and has everything to do with the starting point. So if we have a similar chemical energy diagram, only this one, can I do this? Nope. There we go. Okay, so here now I have 2 different energy diagrams. They start at different energy levels, but they end at the same point. And this is exactly what happens when you burn pentane versus burning isopentane. That one of them is going to start at a higher energy state, and the other one is going to start at a lower energy state. And what that will do is it will create different heats of combustion. I'm going to get out a different amount of energy when I burn. The one that starts at a lower energy state will give me less energy when I burn it. The one that starts at a higher energy state will give me more energy when I burn it because it started off at a higher energy state. So we can go back to the data, and it shows us that the pentane gives off more total energy. And the isopentane, when you burn it, gives off less energy per mole. So if the pentane gives off, I'll make sure I say this right, the pentane gives off more total energy, that means that the pentane is the one that starts at a higher point up here. The pentane starts up here, and the isopentane is the one that starts at a lower energy state. And this again is based on the fact that when I burned the pentane, I got more total energy out of it. When I burned the isopentane, I got less total energy out of it. They both end up at the same point because both of them end up producing 5 molecules of carbon dioxide and 6 molecules of water for every molecule that I burned. The purpose of diagramming all of this and thinking about the question this way is it allows us to experimentally determine that pentane is a higher energy molecule than isopentane. And so for constitutional isomers, remember that constitutional isomers have the same molecular formula. A higher heat of combustion, typically expressed as a delta H, is equal to a higher energy state. And this matters because the higher you are in energy, the less stable you tend to be as a molecule. Less stable / more reactive. So of those two molecules, pentane is a less stable state than isopentane. And that's based on the differences of their heats of combustion. A compound, an isomer, sorry, not a compound, but an isomer with a higher heat of combustion will be a higher energy compound with that is more reactive and less stable. So what about hexane? Hexane has a much, much higher heat of combustion. Does that mean that hexane is much, much less stable? Because the higher energy you have, the less stable you tend to be. And the short answer is no. In fact, we cannot compare, based on heat of combustions, it's not fair to compare molecules that don't have the same number of carbons and hydrogens. And the reason that hexane gives off more energy here is simply because you're doing more total chemistry. You're combining more carbons with more oxygens, more hydrogens with more oxygens, and you're generating more total molecules. So it's just kind of a totally different system, and it's not fair to compare the stability of different molecules based on, unless they have the exact same number of atoms and the same types. So they have to be constitutional isomers for this type of analysis to be valid. But there is one thing you can think about. What if I were to divide this number right here by the number of carbons? And so you can think about with isopentane, you have a delta H. Your delta H is equal to negative 3504 kilojoules per mole. But if you want to think about that in terms of per carbon, so you just divide that by 5. And if we divide that number by 5, we're going to get about 700 kilojoules per mole. And this is now 700 kilojoules per carbon. Now that was kilojoules per mole, and now this one is about 700 kilojoules per carbon. And there's some estimation going on there. With the pentane, the delta H is negative 3509 kilojoules per mole, which is also about 700 kilojoules per carbon. And I'm dividing both of these numbers right here by 5 because there are 5 carbons. In fact, and this is important, it's about a little bit bigger than 700 kilojoules per carbon. If you divide 3504 by 5, you're going to get something a little larger than 700. And the same thing is true right here. But now for the hexane, the delta H is equal to negative 4195 kilojoules per mole. That is pretty close to 4200. If you divide 4200 by 6 carbons, you're also going to end up with 700 kilojoules per carbon. But in this case, because it's less than 4200, it's actually slightly less than 700 kilojoules per carbon. And so while the heat of combustion for hexane is going to be higher overall than pentane and isopentane because it has more carbons, it's actually slightly lower per carbon. So the best way to say this is it's not a good comparison, but based on combustion analysis, hexane is slightly more stable per carbon than pentane and isopentane. And that statement is true across the board for all small alkanes, that the heat of combustion goes up as you add in more carbons, but the stability actually goes up a little bit as well. They become a little bit more stable as you tack more and more carbons onto the system. There is unfortunately a confusing coincidence. This is generally the case that the more branched your alkane, the lower the heat of combustion tends to be when comparing constitutional isomers. So pentane and isopentane have exactly the same chemical formula. They are constitutional isomers of each other, and the isopentane happens to be a lower heat of combustion, and that has to do with the fact that it's more branched. The problem is that students get the rationale confused with boiling point. It has nothing at all to do with stackability. It simply is based on the fact that a more branched compound tends to be more stable, and a more stable compound gives off less heat of combustion. So when you're asked to order compounds based on their heat of combustion, the most important criteria is the number of carbons, and then once you have the same number of carbons, the heat of combustion will be higher for the less branched compound and lower for the more branched compound. So now we're ready to fill in the last of our definitions, the combustion analysis of alkanes, and this allows us to determine stability of constitutional isomers, actually of just isomers in general. There's more types of isomers that we'll talk about later on this semester, and we'll continue to come back to this concept of combustion analysis because it is an easy way to order isomers. You can't just set everything on fire and expect that to be meaningful, but if you carefully burn constitutional isomers and measure the heat that comes off, you can determine which of those isomers is the most stable because it gives off the least amount of energy, and which of those isomers is the least stable because it gives off the most energy when you burn it. I just remembered that I didn't incorporate the energy diagrams for the following reactions, and so we'll need to copy and paste this diagram right here for pentane and isopentane, and we'll kind of drop that down here. And then on the same diagram, if I want to also incorporate hexane, it's not a good idea to put it on the same diagram. And the reason for that is it produces a different number of products, and so we don't know where they end. And so all you really do with the hexane is you just do one of these. We'll just cut this out, cut the pentane out right here, and then redraw the whole thing for hexane. I'll go ahead and stop recording and do that myself. Okay, here's the finished diagram now for hexane. I went ahead and drew in the molecule hexane right here and labeled the delta H value for the hexane, just so I know exactly where the delta H is coming from. If you had taken this same chemical formula, broken off this carbon and moved it, let's say, to this position, then you would be generating a constitutional isomer. I don't know what the name of that would be. If it has a common name, the systematic name would be 2-methylpentane. 2-methylpentane is a constitutional isomer of hexane, and 2-methylpentane is more branched than hexane would be. A more branched isomer generates a lower heat of combustion, so if you were to try to trace in what the energy diagram for 2-methylpentane, the constitutional isomer of hexane, it would end up at the same position, because when you set fire to isomers, they generate the same products, but it would produce less energy. A more branched alkane produces less energy because it would start at a lower energy position. So 2-methylpentane would start here. If you had two branches on there, like 2,2-dimethylbutane, it would start even lower. And the more branches you introduce, the further and further down in energy your starting point goes. resulting in a lower delta H value and a more stable compound, but your ending point still ends up being at the same position.